Hello dear students, today's topic of my lecture is automorphism of groups. Before going on to automorphism, I am just revising you something. You have already, I go through these chapters, homomorphism of group. So first of all, we define the homomorphism mapping. Let there be two group structures. One is G with respect to operation O, other is G dash with respect to star operation, be two groups. Then we defined a mapping F from G to G dash such that this mapping is defined by F of A operation B is equal to FA star FB, where all AB belonging to G. That means what? This mapping F is called a homomorphism if it preserves composition. Composition means what? If we have two elements in the domain G, then their product, you can say A operation B, will be under this mapping we have in G dash FA operation FB, operation of G dash. So this type of property is called composition preservation. If a mapping F from G to another group G dash preserve this type of mapping, then that mapping is called homomorphism. And FG is called homomorphic image of G. If a homomorphism mapping in addition which is onto is called epimorphism. If a homomorphism mapping which is 1-1 is called monomorphism. Similarly, a homomorphism of a group G onto itself, it's called endomorphism. Now we are going to define natural homomorphism. For that, before that, we have defined the normal subgroup, and you know that normal subgroup forms a quotient group or factor group, that is group of all cosets G by H. So let F be a mapping from group G to factor group G by H, which is defined by F of A is equal to HA. HA is the right coset where for all A belonging to H. That is, its image of every element of G goes on to a coset in the range G by H, factor group, set of all cosets. This mapping is homomorphism, and this type of homomorphism is called natural homomorphism or canonical homomorphism. Now I am discussing some example. The very first example, you can see if defined a function or mapping fx is equal to E. This mapping is such that it takes all the elements of domain into the identity element of range. Then this mapping is a homomorphism mapping. We can easily check it out, and this type of this mapping is a homomorphism mapping. One more example I am going to take, and let us consider a group of all real numbers under addition. You know it, we have discussed it, that the R plus forms a group, and G dash be the multiplicative group of non-zero real numbers with respect to R0 dot. We have already discussed that for real number to form a multiplicative group, we have to delete, we have to take all the non-zero elements. So now we take a mapping F from G to G dash, where G is R plus and G dash is R0 dot. This mapping is defined by, it takes all the elements of G, FA is equal to 2 to the power A, where A belongs to G. This mapping is homomorphism. So for that, we have to show it preserves composition. So consider A and B two elements of G. So this implies by closure law, because this R plus is a group, so under addition A plus B will be in G. And now we take the mapping of A plus B, A composition B. This mapping by definition of mapping will be equal to 2 to the power A plus B, and this is 2 to the power A into 2 to the power B, and 2 to the power A is FA and 2 to the power B is FB. So this F of A plus B is equal to FA into FB. That means this mapping preserves composition between the two groups. So it is a homomorphism mapping. One more example I am going to take. For this, you have to take G be the group of all group under addition, and we take G dash equal to G. So this is a mapping from G to G dash. You can say it is from G to G, which is different. by fx is equal to 2x. So if fx and x and y are any two elements of G, which are arbitrary element, so composition of group is addition in both domain and range. So we consider f of x plus y. This, by the definition of the mapping, it will be equal to 2x plus y. So this will be easily to say 2x plus 2y, and this is by the definition equal to fx plus fy. So it preserves composition, so it is also a homomorphism. So I have discussed some of the examples of homomorphism. Now, very important part of homomorphism mapping, that is a kernel of homomorphism. So if f from G to G dash be a homomorphism mapping, then kernel of f is denoted by kf, is defined as the set of all those elements of G or domain which are mapped onto the identity element of range. If we take E be the identity element in G and E dash be the identity element in G dash, then the set of all those elements which are mapped onto the identity element of G dash, that is range, is called kernel of homomorphism. You can mathematically define this set as set of all those elements of G such that fx is equal to E dash, where E dash is the identity element of G dash. This space is also known as null space. So this is about the kernel of homomorphism. You have already heard about it in previous classes. And now isomorphism. You know, if G with this operation O and G dash with star be two groups, then a mapping from G to G dash is said to be isomorphism if it is homomorphism with 1, 1 and onto. That is a homomorphism which is also EP and monomorphism. It is called isomorphism. So easy to say, this mapping F is 1, 1 onto and composition preserving. Then that type of mapping is called isomorphism mapping, and these two groups are called isomorphic group, and they are denoted by this. Now we have an isomorphic group onto itself. We have previously defined isomorphism over G and G dash. If G dash is equal to G, then that type of mapping is called automorphism. We will discuss about it in this chapter. And now I have some of important properties of homomorphism mapping. The first property you have already seen in previous classes, that identity element of domain always mapped onto the identity element of range. And A inverse, the image of A inverse in G will be equal to FA inverse. Second property is a homomorphism F is a group into a group G dash is a isomorphic if and only if, I have already told you that isomorphism, if the homomorphism become isomorphism if it is 1, 1 and onto. If it is 1, 1, then kernel will have only one singleton element, and that element is E. So if kernel of F is E, then that mapping is isomorphism. So if F is a homomorphism of a group G into a group G dash, then kernel K is a normal subgroup of G. This is a very important property proved earlier. If next property is what? If F is a homomorphism of a group G into a group G dash with kernel K, and A be any arbitrary element of G such that FA is equal to A dash, where A dash belongs to G dash, then the set of all those elements of G which have the image A dash in G dash is coset KA, coset KA of K on G. And one more property, if G be a group and N be a normal subgroup of G, you know if every normal subgroup of G forms a factor group or quotient group, we define the mapping F from G to G by N, denoted by Fx is equal to Nx for all x belonging to G. Then F is a homomorphism of G onto G by N, and kernel of F is equal to N. This is a very important property. So these are the some definitions and properties which we have to use in this chapter, automorphism of group. Now we start the automorphism or structure of groups. So we have already defined it, an isomorphism of a group onto itself. That is a mapping F from G to G dash, which is isomorphism. Isomorphism means what? It is a homomorphism, that is composition preserving, and it is also 1, 1 and onto. So a isomorphism mapping of a group onto itself is called an automorphism mapping. That is, if F is a mapping from G to G, then F is 1, 1, onto and composition preserving. If we take group as multiplicative group, then we can easily see that the mapping F will be automorphism if it is 1, 1, it is onto, and for all A and B belonging to G, F of A dot B is equal to FA dot FB, where G is multiplicative group. So this type of mapping is called automorphism. Now we are going to discuss some of the examples. I have already explained one multiplicative group in the very first lecture, definition and examples. The most important multiplicative group is 1 minus 1 I minus I, and you can see here we have taken a permutation of this group, and it is easy to see that this forms a automorphism. We can define a mapping between these groups, and which mapping is 1, 1, onto and composition preserving. So this is an example of automorphism. One more example, you know the set of all complex number forms an additive group. So we defined a mapping F from C to C. C is the set of all complex number, which is defined by Fz is equal to Z bar, where Z belongs to complex number and Z bar is complex conjugate of Z. You know the complex conjugate. If Z is equal to X plus Iy, then Z bar will be X minus Iy. So this type of mapping where Fz associate Fz bar is also a automorphism. We can easily see it, and this automorphism is called this mapping is automorphism. This is a second example of automorphism. Now we are going to show the first theorem. If G be a group, then a mapping which associate to each element A belonging to G to its inverse A dash A inverse is a automorphism of G if and only if G is abelian. One more explanation to this theorem, that is, if G be a group, then a mapping which associate each element of G, that is, you can say A, by its inverse, then that mapping is automorphism if and only if G is abelian. So we have to prove both the parts of this theorem. So first we assume that G is an abelian group, and now we defined a mapping F from G to G dash, G to G, because here we are defining automorphism, and automorphism is an isomorphism mapping between the two same groups. So G to G be a mapping defined by Fa is equal to A inverse. This is the definition of a mapping. It associates each element with its inverse. So this is F of A is equal to A inverse for all A belonging to G. Now we have to show this F is an automorphism. So for that we have to show this F mapping is isomorphism, and for isomorphism we have to show it is 1, 1, it is onto, and it preserves composition. So first we show it is 1, 1 mapping. So you know about if A and B are any two arbitrary elements of G, then by definition 1, the image of A is Fa, Fa is equal to A inverse. The image of B is Fb, Fb is equal to B inverse. So now we consider Fa is equal to Fb, and if we are able to show A equal to B, then this type of mapping is called 1, 1. So consider Fa is equal to Fb, and by definition A inverse is equal to B inverse. So taking inverse on both sides, so this will be equal to A inverse whole inverse is equal to B inverse whole inverse. And you know the basic properties of group. Inverse of inverse is an element itself, so it will be equal to A, and this will be equal to B. So if we take Fa equal to Fb, then this will be equal to A equal to B. This implies that F is 1, 1. Now we have to show F is onto. You know a mapping is said to be onto when there exists no element unmapped in the range set. That is what all the elements of codomain or range are some images of some element of domain. So we take A be any arbitrary element of that range G. So this implies, since this is the basic property of axioms of group, the existence of inverse. So for each A there exists A inverse in G, such that we can say the image of f of A inverse will be A inverse inverse, and that is A. So there exists, each element of range is image of some element of domain. So that mapping is onto. Now we are going to show the mapping F preserves composition. For that, consider A and B be any two arbitrary element of G. So this implies by closure law AB will belong to G. Now we see the image of F under this AB. The FAB will be what? Will be, the definition of mapping is what? Is associate each element with its inverse. So FAB will be equal to AB whole inverse. And we have seen the basic properties of group in where we have shown reversal law, and by using that reversal law, this is AB inverse will be equal to B inverse A inverse. And since the group is abelian, so we can write B inverse A inverse equal to A inverse B inverse. And since A inverse is equal to FA and B inverse is equal to FB, so we have shown that FAB is equal to FA into FB. So this implies F preserves composition. So this implies F is an isomorphism because it is 1-1, onto, and composition preserving. Since this isomorphism is from a group G onto itself, so this type of isomorphism will be a automorphism. Clear? So we have taken this mapping which associate each element with its inverse, and we easily have proved that this mapping is an isomorphism mapping. So it is an automorphism mapping, but we have used one thing, that G is abelian. We have used that property. That is the statement of theorem that this mapping will be automorphism if and only if G is abelian. So we have taken G abelian and show that the mapping is automorphism. Now conversely, what we have to show, we will assume that this mapping is automorphism. That is, between the same group, it associates each element with its inverse, and this mapping is automorphism, and we have to show G is abelian, right? So now F is a mapping from G to G defined by this, already have taken. Let it be a automorphism mapping. Now we have to show that for the converse part of the theorem that this G is abelian. So for that, let A and B be any two arbitrary elements of G. So AB is equal to, you can write AB as A inverse to inverse and B inverse to inverse without any problem. And you know A inverse is FA. So A inverse to inverse will be FA inverse, and B inverse to inverse will be FB inverse. So as this mapping preserves composition, so we have FAB is equal to FA into FB. So FA inverse into FB inverse will be equal to F of A inverse into B inverse. So this is F of A inverse, B inverse, and now we use the reversal law, which says A inverse, B inverse equal to BA whole inverse. So this will be BA whole inverse. And now by the definition of mapping, it associate each element to its inverse. So it will be equal to BA inverse to the inverse, and inverse of inverse will be equal to BA. So we have taken AB and proved AB is equal to BA. So that shows this mapping is abelian, since this is the commutative law held by the group. So this mapping is abelian. This group is abelian. So we have proved both the parts of the theorem. Now we discuss, what about the automorphism? Now we are going to define inner automorphism. Let G be a group and A be any arbitrary element but fixed element. We have taken arbitrary element, but that arbitrary element is fixed, certain element in that group G. So now we defined a mapping which is denoted by F of A, and this mapping is from G to G, defined by FAX is equal to A inverse XA for all X belonging to G. This is the definition of mapping. So this mapping is an automorphism mapping, and this type of automorphism mapping over a fixed element of group G is called inner automorphism. So first we show this mapping is automorphism, and for that we have to show that this mapping is isomorphism. And for to prove this mapping is isomorphism, we have to show FA is 1, 1, onto, and composition preserving. So first we show FA is 1, 1. So for that, let X and Y belongs to G be any two elements, two arbitrary elements of group G. X and Y be any two arbitrary elements of group G. So now we take FAX equal to FAY. So by equation 1, FAX is equal to A inverse XA. So you can easily say A inverse XA, and this FAY will be A inverse YA. And you can take two steps and use, first of all, you have to use the associativity, and then you can use left and right cancellation law, and you will get X equal to Y. It is very easy to prove. So that shows we have taken FAX equal to FAY, and we have proved that X equal to Y. This implies FA is 1, 1. Now we have to show FA is onto. Let X be any arbitrary element of the codomain or range G. So this implies there exists AX A inverse belonging to G. We have to show let AX A inverse is equal to capital X. So FA of AX A inverse will be equal to FAX. So this is equal to A inverse capital XA, and this will be what? A inverse AX A inverse A. So by using associativity, you can write it as this. You have to change the brackets, the G2 of group axioms, associativity. And also you know that A inverse A is equal to E, the existence of inverse, where E is the identity of the group. So here this is from G4, and identity, the property of identity, it can be applied on X. On both sides you will get X. So what we have shown that FA of X A in X inverse equal to X. So that means for every element of range is image of some element of domain. So that implies FA is onto. Now to show it as automorphism, and this type of automorphism is called inner automorphism, we have to show it preserves composition. So for this, let X and Y be any two arbitrary elements of G, and such that FA of XY will be equal to A inverse XY A, and let it be capital X. So it will be equal to what? A inverse, you can write X as XE because XE is identity element. So by multiplying identity element by any element, it will not change. So we can write X by XE by A. So now this will be equal to, you can write E as A inverse. This is the definition of identity. A inverse is inverse of A. So you can write in place of E, A inverse. And now by associativity, you can write it as FA A inverse XA and A inverse YA. And by definition 1, this A inverse XA is equal to FAX, and this A inverse YA is equal to FAY. So that means what? FA preserves composition. So this implies FA is a mapping which is 1, 1, onto, and composition preserving. So it is an isomorphism mapping. Since isomorphism mapping of a group G onto itself is called automorphism, so it is an automorphism. And this type of automorphism, which is taken for any fixed element A of G, is called inner automorphism under this definition that FAX is equal to X inverse AX. So this type of automorphism is called inner automorphism. So this is just some introduction to automorphism of groups and inner automorphism. So that's all for this lecture. I hope you all understand. So goodbye.